Vector A. That's vector B. You know where vector A cross B is? People are doing this right now. I saw at least 2 or 3 people go like that. Vector A cross B, all right, will be orthogonal to vector A and orthogonal to vector B.
Or like a parallelogram, right?
Right? Yes, that's what we'll get to. We'll prove that too. But let me just say this again. You go, what is the cross product of 2 vectors? Well, it is a vector, but that vector will be orthogonal to both of them. Now, if you're curious, well, they went like this. And what they're saying is that vector could be pointed up, right? But in some cases, the vector might be pointed what?
Down.
Down. So does anybody know how you know the difference?
Minus.
For A cross B, there's something called the right-hand rule. I don't know if you like it or not. I'm going to use the tips of my right hand. And if that's vector A and that's vector B, here I'll slide them next to each other like that. Let me make them a little closer. And I will take the tip of my finger in the blue marker, vector A, turns towards vector B, and I'm going to watch the arrow of my thumb. My thumb will point in the vector of A cross B. So which way is vector A cross B going? Up. So which way is vector B cross A going? Down. You got it. That's called the right-hand rule. Right? That's the right-hand rule. Just start with the vector and turn the other way.
Can you do the B cross A for a second?
So yeah, so if this is A and that's B, and I use the right-hand ruler, I'll use the tips of my fingers, start at A, and curl towards vector B, and just watch my thumb. My thumb will point in the direction of A cross B.
Okay, great.
But now, where will vector B cross A be?
Okay, gotcha.
Wouldn't it have to be totally opposite? And it's kind of weird, you're like, ugh. Like, it looks like that, but it would be opposite directions. So A cross B and B cross A, just going to be opposite vectors, aren't they? They'll have the same, but they'll be opposite vectors. Well, to do this, we need a couple vectors. So let's just use, how about vector A is 1, 2, and 4. Vector B is, let's just use 3, 0, -2. I'm putting them in component form. And can we find A cross B? To do this, it's finding the determinant of a matrix. Don't worry if you've never worked with matrices before. But I'm going to write a matrix like this. We're going to find the determinant I, J, K. I'll just put that up in the top row. Because it's A cross B, I'm going to list vector A here. 1, 2, 4. And then I'm going to put vector B here. And you'll see this on my formula sheet. That I said the determinant of A cross B will be vector A cross B. So what we're doing right now is we're going to find the determinant of this matrix. It's not hard to do without a calculator. Okay? So here's a matrix. We're going to find the determinant of this matrix. It will be A cross B. I just put I, J, K here. If you want to put little arrows on here, you can. There's the components of vector A. There's the components of vector B. Here's how you find the determinant of this 3 by 3 matrix. Does everyone know it's a 3 by 3 matrix? For the first component, this is what you do. And we'll do this all the time in our course. So get ready. If you've never done this before, you'll be doing this a lot in our course. For the first component, I want you to wipe out the first column. And then do this times this, all right, minus this times this. Let me do it again with the this and that. This times this minus this times this. So if you prefer, I've got like an A and a B and a C and a D. I need to find AD minus BC. When you hide, which column?
First column.
First column. And you go, what do we find? It's just called the determinant of a matrix, but it will give us this actual cross product. So what's the first component? What's -4 minus 0?
-4.
Negative. Don't see that? I just want to point out what I did. I did 2 times -2 minus 4 times 0. If you want to write that out, somebody might have to go, well, it's the first time I ever did that. So right here, you might be writing, I did 2 times -2 minus 4 times 0, right? But I'm just going to repeat this process. Come down to the third component. Come all the way, let's go to the third one next. semester, what are you doing? Come on down to the third, let's go down to the third component. For this component, wipe out which column?
Third.
Third column. AD minus BC. 1 times 0 minus 2 times 3.
Oh, so the component that we are trying to look for, you have to hide that component.
That's right. And repeat that. He says the component you're trying to find, you hide that column. And then, you just deal with these 4 numbers, and it's always AD minus the product of BC. So what do you get for the third component?
It is
0 minus 6 is?
Negative 6.
Right. Now, and I know we're looking at this with our eyes, and sometimes I get tired, and I look at the wrong column, so I want to show you how we can check this and get some suggestions from the class. There's something about the definition of the determinant of the matrix, you got to be careful with the middle column. Do the same thing in the middle column, except change the final sign. Let me repeat that. Do the same thing, this is why I did this one last. Same thing, but your final result, I need you to change the sign or whatever you get. So I'll get a negative ready right now. So here I go. Wipe out the middle column, AD
Negative 2.
minus BC. What is negative 2 minus 12?
Negative 14.
So I get negative 14, but I said take the
Minus.
star and opposite, right? And what's the opposite of negative 14?
Plus 14.
Now, because you and I were doing this in our head, mentally, and we wrote stuff on the paper, we're doing all this math, I highly recommend checking this. Because I could have looked at the wrong column, everyone. Or you heard this, when you do minus 12, minus 2, minus 5, we can accidentally add rather than subtract. Let's be careful. What's a way I can check? Let's go back. What's the definition of a vector? We said, well, it's always going to be what? A cross B, it will be perpendicular. So, what should be the dot product of this vector and this vector? 0. I would check it. Since we did all that math, dot products are easy to check. So, here I go. Is negative 4 plus 28 plus negative 24 equal to 0? And that's something you can do in your head. I know you can. Is that equal to 0?
Yep.
Yep. I don't know how to spell yep. Is it yep or yep? Something like that, right? Yeah. But also check this one too. I always check this real quick, because I can check it really quick mentally. Is negative 12 plus 0 plus a positive 12 equal to 0. Now you're absolutely 100% sure you found the right cross product, right? You got it. Cool. And by the way, if that's A cross B, can we just write down here, what would B cross A be? It would just be, take all these and change the what? Wouldn't you just get this?
Change the sign.
Hey, on that note, the problem I was talking about on the last part, it goes, which of the following vectors is perpendicular to both of these? You might find it easier to just get the cross product, right? So I wanted to reflect back to number 9. The question, which one of the following vectors is perpendicular to both of these? You might just go, let me get the cross product, because the cross product has to be what? Perpendicular to both of them. Sure. But you already had an approach, so feel free to do it that way. Cool. I don't know if I have it on this sheet, but I want you to be careful about one thing. I know there's a problem in a textbook with this. They give you 2 vectors, and they go, can you find 2 vectors, right, that are orthogonal to this? Well, this is what we do, right? This would be one of them, this would be the other. But they inserted the word unit vector. So let me say this again. The real question, it's in the book. I'll look to see if I have it on my sheet. But it's a textbook problem. They go, can you find 2 unit vectors that are orthogonal to both of these? The first step would be, do this, get your vectors, and then what would be the last step? Just turn them into what? Unit vectors. There you go. So I just want to point that out. So just be careful when you see that word unit. I'm looking right now over our practice set. I don't see it anywhere in the practice set where they did that. Cool. All right. Hey, well, let's keep going with this. Let's keep going with this. The cross product is huge. We know that A cross B is a vector. It's defined as the determinant of a matrix, right? So I can write the formula like this. It's I, J, K. But which components did I put first? the components of A, and then what did I put second?
B.
And maybe I'll just go like that, but it's always gonna be that, I didn't write out the long what? This times this minus this times this, the book does that. I think it's easier if we just wipe out the columns and do it like we do a determinant. Okay, so I just write it like that on my sheet. But there's another formula that's like this. So I'm gonna put it in yellow and put it right underneath this, okay? Here you go. What is the magnitude of A cross B equal to? All right, it looks like this, but I want to put a magnitude around it. It's equal to the magnitude of A times the magnitude of B times the sine of theta, where the angle theta is the angle between those two vectors. Doesn't it look like the other one?
Mm-hmm.
Just make sure you have a magnitude around the A cross B. So let me write that again. When the magnitude of A cross B is equal to magnitude of A, magnitude of B times the sine of what? Sine. Cool. Well, I was wondering if you could help me prove something. Can you help me prove? Oh, math proof. It only take a second. That when the magnitude of A cross B will equal the area of a parallelogram occupied by those two vectors. Oh, this one won't take too long, so let's draw a picture of a parallelogram. Quick proof. Let's call this vector A, and let's call this vector B down here. Now, when all parallelograms do have a height, we can just call the height h. And let's put an angle theta right there. Can you just help me prove that this magnitude of A cross B, I know it's equal to this, but can we use this theorem to help us prove that the magnitude of A cross B will be equal to the area of this parallelogram? All right? Sure, we can do this. Just involves a little trigonometry. Let me start with geometry. What's the area of a parallelogram? Base times height. What's the base? B. Well, it'd be the length of B, right? So I'll put magnitude of B. What's the height? That's h. And we're getting closer. Can you help me substitute something for the h in that image? Do a little SOHCAHTOA. I know. What's the sine of theta? What's the sine of theta? It's opposite over hypotenuse. And I'll put a length for length of A, right? So what's h equal to? H is the length of vector A times sine theta. Work out with this. I just want to show you, you can actually derive all this stuff. And look what we get. Ta-da! We're done. We've done our proof because we used that theorem. This is equal to the area of a what? Parallelogram. Cool. Hey, on that note, isn't every parallelogram just broken into two triangles?
Mm-hmm.
So what's the area of a triangle?
Half base into height.
Same thing, but what do you got to divide? What do you got to divide that by?
Divided by
How many
2.
triangles in a parallelogram?
2.
2, right? There's vector A, there's vector B. It'll just be the magnitude of A cross B divided by F.
2.
So can we do one of those? Ellen, can I give you 3 points? And from the 3 points, see, think about this. This is that problem. You got a younger brother. They're taking like an honors geometry class, and they're given something like this, and they're spending all this time on it. You might say to them, "Well, that problem's simple with vectors because of this." I mean, seriously, with vectors and cross products, it's easy to find things like, oh, that angle in three-dimensional space, or to find the area of a triangle in three-dimensional space. It's the way to go. So let's try that. Thanks for being being patient with our nice little proof there. But the area of a triangle is this. So let's see. We've got to pick 3 points. P, Q, and R. What's this? That's 0, 1, 2. This is 3, 1, 1. And that's 2, 0, 3. Can you find the area of the triangle occupied by those 3 points? Okay, let's go find the area. These points are all over the place in space. So what I'm saying is in that honors geometry class, the students carefully plot these what? These points, and they're looking for maybe right triangles or something. Right? Maybe they're trying to use law of sines or something like this. We're saying, heck, you need the area of this? Use vectors. Use vectors. So, want to use vectors PQ? What's that? What's vector PQ?
It is 3.
Just be careful, I always say this. Points look like vectors. Points look like vectors. Be careful, don't cross points. True? That's right, go, oh no! You crossed points, can't cross points. PQ is what?
3, 0, negative 1.
Okay. What's PR?
Here is 2, negative 1, 1.
Okay. And then you gotta cross these, huh?
Uh-huh.
So I'll just go like this. I take your I, J, and K, and here we go. Let's cross them. Here comes PQ cross PR. Right here. Ready to do this? What's 0 minus 1?
Minus 1.
0 minus a positive 1. Come down to the third column. Come all the way down to the third column. What's negative 3 minus 0? Cool. What do you do in the middle column? Something special?
You have to change the sign for negative
Get
4.
that ready. Get it ready. Get ready. Change the sign. Do the same thing, but change the sign. Here's my yellow chalk.